SOURCE is a 3-year EU research and innovation project under the Horizon 2020 scheme, led by Universität Pompeu Fabra. The consortium is made up of industrial partners, Foundry, DNEG and Disney Research Studios, and university partners BRNO University of Technology, Film Academy Baden-Württemberg, Saarlandes University and Trinity College Dublin. SOURCE set out to increase efficiency in the creative sector, be that post-production, virtual production or games. We looked at future-focused technologies such as light fields, as well as improvements to modern pipelines and specific use cases that will help the artists and studios of today, all with the aim of saving time and money for an industry which is constantly being pushed to do things faster, to a higher quality while remaining cost-effective. The University of Saarlandes, BRNO University of Technology and Trinity College Dublin created an end-to-end light field showcase, recording, processing and transforming light fields, showcased in the Unfolding and Unfolding 2.0 productions, produced and edited at Film Academy. As this technology develops, it will become easier and cheaper for productions to take advantage of these new workflows in ways that the SOURCE project has prototyped. Finding, classifying and storing assets can be a significant challenge in an industry where technology and requirements are constantly advancing. DNEG, Foundry and Disney Research Studios have created a fully extensible and interoperable asset library, including Asset Store, Classification and Transformation Framework, as well as machine learning classifiers. This framework means an artist can be anywhere in the world and have fast and easy remote access to this powerful asset reuse pipeline. This was showcased by the LED test carried out by Film Academy. IP4EC Research Group at UPF built tools to maintain colour integrity across different display types, viewing conditions and viewers. They also developed tools that can recontextualise the colour of assets so they can be reused in different stylistic projects. Trinity College Dublin, GTI Group at UPF and DNEG, as well as former partner Iconema, all focused on improving crowd tours. They did this by adding machine learning so that crowd agents could interact with the scene and in different stylistic manners. This work was incorporated into Film Academy's Virtual Production Editing Tools, or VPET, as well as UPF's web tools. DNEG created a suite of tools to improve the control an artist has over crowd placement and trajectory. These improvements mean that crowd assets can be reused in different contexts. The SOURCE project is committed to encouraging asset reuse in the creative community and has provided a host of Creative Commons assets such as Lightfield Element Shoot, Semantic Animation Library and free Miniature City assets, In Love and 50 Megatons, as well as publishing a white paper describing the consortium's use of smart assets and recommendations for continued development. The SOURCE project is funded under the European Union's Horizon 2020 Research and Innovation Programme.
Hello and welcome to another FMX Spotlight. My name is Volker Helzle. I run the Research and Development Group of Film Academy's Animationsinstitut and I will be your host for tonight's show. The FMX Spotlight program is intended to bridge the gap until FMX 2021 Reimagine Tomorrow, which will take place May 4th till May 6th as an online event. Today we will hear and see details from a research project funded by the European Union. Project SOURCE, Smart Assets for Reuse in Creative Environments, is a collaborative project between 8 companies and academic institutions from all over Europe. Its goal is to produce, pilot and demonstrate a set of professional tools and techniques that reduce the costs for the production of enhanced digital content for the creative industries by increasing the potential for repurposing and reuse of content, as well as providing significantly improved technologies for digital content production and management. We have prepared a very comprehensive presentation for you and a Zoom room for a Q&A session right afterwards. So without further ado, let's head over to Perry Friend from Foundry, who will give us a detailed introduction on the project.
Thank you, Volker, and hello and welcome to the Source project. My name is Perry Friend and I work at Foundry. So what is Source? It is smart assets for reuse in creative environments. Today, you'll hear from our Source Consortium partners on how we are increasing efficiency in the creative sector through asset repurpose and reuse. You'll hear from University of Saarlandes, University of BRNO and Trinity College Dublin, who have been researching and developing methods of generating smart world views by capturing and processing light fields, with the aim of making them usable for media production pipelines. We then switch to a pipeline focus, where my colleagues at Foundry, along with Disney Research Studios, the IP4 EC Group at Pompey Fabry University and DNEG explain how they have been developing a storage system for smart assets that combines local and cloud storage, as well as finding and transforming assets using deep learning and semantic labeling techniques, enabling them to be used for new contexts, purposes, users, and environments. Finally, we move to crowds and semantic animation, where the crowd team at DNEG, the vSense team at Trinity College Dublin, the GTI team at Pompey Fabry University and Film Academy will demonstrate real-time control systems for authoring animated content using smart assets, automatically synthesizing new scenes from existing ones, and integrating smart assets into virtual production scenarios. They have prototyped these technologies and toolkits in a series of experimental productions, evaluating their performance in realistic contexts of professional use. None of what you hear today would be possible without the funding of the European Union's Horizon 2020 Research and Innovation Programme. So, without further ado, let's kick off with Thorsten at University of Saarlandes.
Thank you very much, Perry, and welcome everybody to the introduction of the Source contribution by Saarlandes University. Source starts with smart assets. So we've created 4.5D light field videos, the elements and unfolding, and 5D light field videos with the hard toy set. We've established the pipeline for the integration into production workflows, including pre-processing steps and the transcoding into image and video formats. And we've served the partners' needs by maintaining a large storage area with externally accessible cache and preparing assets in various formats. In Source, we used our unique self-built 5D light field array. This array has been available at the beginning of Source, but has been used semi-professionally for the first time. The data rate is roughly 9 gigabytes per second in raw format and is stored on an external storage with 350 terabytes. We've ported the array to Ludwigsburg and the Saarländische Rundfunk. Our unique characteristics are very short exposure times down to a few 10 microseconds and a fully programmable sync plane. The baseline is set up with 70 mm, allowing for scene sizes of roughly 2 meter in 2 meters distance. Share with us some impressions from the shooting of the 4.5D light field video sequence Unfolding. We very much thank Saarländischer Rundfunk for offering us their studio for this capture.
Okay, und Ton ab. Okay, danke nochmal, Kat.
For the demonstration of 5D light field videos, we created the Hartoy scene. This scene contains a lot of very fast motions like the spinning CD-ROM and the child's spin top, and offers the possibility to show and demonstrate what 5D light field video capture can offer. To demonstrate the advantages of 5D light field video, we zoom into certain parts of the Hartoy sequence. The sequence is shot with 40 frames per second, but 4 subframes, so that virtually 160 frames per second are created. The CD-ROM shown on the top left spins with 2400 rounds per minute, meaning that the CD turns exactly 90 degrees per subframe or 360 degrees per frame. By introducing this fifth dimension into the capturing, we indeed can capture the entire surface of the CD-ROM each and every frame. Same holds true for the child spin top on the right side of the image, which is captured in 4 different motion phases. To enable sharp imagery, the exposure time in these captures has been very short, with 350 microseconds. To enable the inclusion of light fields into standard production workflows, we've exported our assets into OpenEXR and Adobe PSD and enabled the integration into standard tools like Nuke. We've also participated in the standardization through the JPEG Plano group, which standardizes 4D light fields, and we will contribute our Hartoy 4D light field scene plus disparity maps. Higher compression ratios can be achieved by using video codecs for light field encoding. We've developed a compression of light field subframes with automatic generation of per frame customized coding structures for predictive HEVC/H.265. The prediction buffers are carefully filled with spatial as well as temporal neighbors so that the prediction itself can be optimized. The full pipeline consists of the calibration, the debayering that produces full color images, the color correction that aligns the colors between the different cameras, and the rectification. We capture images in raw data with a resolution of 1920 x 1200. We demosaic the sensor data to retrieve the full color range. And of course, this has to be repeated for all 64 cameras in the array. We align the colors between the different cameras, and we rectify the images to correct camera alignment errors. Thank you very much, and with this, I invite Marek to introduce the contributions from BRNO Technical University.
Thank you, Thorsten. I am Marek from BRNO University of Technology, and I will present camera array calibration and the method for real-time light field data refocusing, which we developed for the SOURCE project. The multi-camera array consists of multiple synchronized cameras arranged in a grid pattern. Due to the manual setup of the array, some small misalignments of the cameras, either in position or in rotation, can occur. Estimating those errors and preprocessing the image data according to computed parameters can improve the results of algorithms working with the light field data. The process of estimation of camera parameters, such as their positions and orientations, is called calibration. It is performed either by using a calibration object with known geometry or by exploiting the relations between the camera and the scene. We use the latter approach based on the observation of structured scene with additional constraints given by the camera grid array. The relations between cameras and a scene are estimated using the structure from motion pipeline. The calibration requires images of a scene from each camera at the same time frame. The estimation of a relative pose between two cameras requires a set of reliable 2D correspondences. Those are extracted using feature detectors such as SIFT or SURF. The matching pairs are found by analyzing metrics between all possible feature point combinations, and the pairs with high scores are selected. This process is repeated for all camera pairs, so the sets of corresponding points are known for each camera pair. Based on the projective camera model and epipolar geometry, the relative camera poses can be estimated. And then, using the poses and 2D point correspondences, triangulation algorithms can be applied to compute the 3D scene structure. The most important part of the calibration process is the refinement or optimization. Refinement aims to minimize the error between estimated state of the system and observed state. In computer science, the optimization problem that minimizes the distances between predicted and observed 2D points is known as bundle adjustment. But in our case, we can set additional constraints on the optimization because of the grid structure. We utilize a hypergraph structure to represent the optimization problem. The configuration of the system consists of variables, those are sensor poses and 3D structure points. Each variable is defined by a number of parameters according to the number of its degrees of freedom. The initial estimation of the variables is provided by the structure from motion pipeline. The measurements impose relations between the variables. They are represented by edges connecting the variables that are involved in the measurement. Each edge gives rise to a residual, and the goal of the optimizer is to find the configuration of the variables that minimizes the sum of squared residuals by solving the nonlinear least squares problem. In our system, we have measurements of the 2D point reprojections, the measurements of absolute position of cameras in a grid, and measurements of baseline distances between the cameras. To solve the system of nonlinear equations, we use the SLAM++, which is an open source nonlinear graph optimization library developed at BRNO University of Technology. SLAM++ implements several very efficient nonlinear least square solvers based on fast sparse matrix manipulation for solving the linearized problems. The modular design also allows for simple implementation of custom edges, which in our case are the grid constraints. SLAM++ produces fast but accurate estimations, which most of the time outperform similar state-of-the-art implementations of graph optimization systems. So, after the calibration process is done, the images can be rectified using the computed camera parameters. This allows further use of the data, for example for quick shift sum algorithm, which offsets the images and sums them to achieve the refocusing effect. Real-time per pixel focusing method allows production of refocusing effect without the artifacts that are present in shift sum approaches, which are caused by discrete representation of light field. The method works without having the 3D model of a scene, without depth maps, or without the need to interpolate between images. It creates a focus map, which is an image where for each pixel the refocus information is stored. And the refocusing effect works in two steps. First is the creation of a focus map, And in second step, the final image is composed using the focus map. The weighted shift-sum algorithm is used to generate new views in various focusing distances, exploiting the fact that when focusing distance is iteratively increased, every pixel is in certain iteration in focus. For each pixel, a variance is computing during the summation between pixel values. At the end, the pixel with the lowest variance value is chosen and the corresponding focusing distance is stored in the focus map. To keep the computation real-time, we utilize computations and parallelism available on GPUs. The focus map generation is performed in the compute shader, and each thread is computing one focusing distance. Focus map generation and final image composition steps are separated, so each one can produce the final result in different resolution. The advantage of this approach is the experimentally proven fact that focus map resolution can be reduced to achieve better performance without significant quality loss, which is the key for real-time usage. We evaluated the method on multiple light field datasets in different resolutions. The focus map estimation and image composition takes 15 to 18 milliseconds, which can be further accelerated by computing the focus map in lower resolution. Thank you for your attention, and the next speaker will be Alain from Trinity College Dublin.
Thank you, Marek, and hello everyone. My name is Alain, and I'm a postdoctoral researcher in the Vicent project led by Professor Alyosha Smolich at Trinity College Dublin, Ireland. We are a team of more than 20 researchers in visual computing at the intersection of computer vision, computer graphics, and media signal processing. And one of our main research direction is light field imaging. So I'm now going to present our contributions to the SOS project, where our main role was to provide processing tools for the smart reuse of light field assets. Note that most of these tools are publicly available on our GitHub page. Before I start the presentation, I also want to thank my colleagues who contributed to this work through the duration of the SOS project. Light field imaging has been an active research topic for around 25 years now, and it has a wide range of applications from low-level processing, typically right after the light field capture, that can be, for example, color correction or super resolution, to high-level applications such as view synthesis, refocusing, or display. And then there is everything that is in between, that can be compression and streaming or depth estimation. And this wide range of application is what makes light field such a smart asset. And the light field processing tools I'm going to present now cover most of that application range. Among the first tools that we developed, there are decoding and post-processing tools for plenoptic cameras, like the Litro Illum shown here on the left. Compared to traditional cameras, plenoptic cameras have a micro-lens array inserted in between the main lens and the sensor, which allows to capture light rays coming from different angles. But this design comes with some limitations, as the whole spatial angular information is multiplexed on a single sensor. So the individual viewpoint images have a fairly low spatial resolution, and are also noisier than the image captured with a traditional camera. In addition, there are known color inconsistencies in between the different views. In order to address these limitations, we propose a pipeline for enhancing the quality of light fields captured with the plenoptic camera. While some aspects of this pipeline are quite specific to the Litro Illum camera, such as raw image multiplexing, other tools in these pipelines are more generic and can be applied to different types of light fields. Here we show some results obtained with our pipeline. We can see that compared to existing decoding tools shown on the left, our proposed raw demultiplexing in the middle has very different colors, which are much closer to the natural colors of the scene, but are not consistent among the different views. And this is corrected by our recoloring tool, as we can see in the final results on the right. Note that color inconsistencies can also be found in light fields captured with camera arrays, as discussed in the previous presentations. So we adapted the recoloring tool from the enhancement pipeline to address this issue as well. And this tool was used to correct light fields assets captured during the SOS project. As I mentioned earlier, light fields captured with a plenoptic camera can suffer from noise. Thus, at the end of our enhancement pipeline, we have a denoising step. In this example, we have on the left the output of the recoloring step, which is quite noisy, and on the right, the denoise results. For denoising, we use the LFPM5D filter, which we had developed earlier, which takes advantage of the natural sparsity of light field patches in the 5D transform domain. In addition to our enhancement pipeline, the LFPM5D can also be applied to light fields capture with different acquisition systems, such as the gantry dataset from Stanford, shown here, and by extension, the camera arrays. Here, synthetic noise was added to the images in order to test the LFPM5D performance for different noise levels. And we can see that even with high noise level, we can restore the light field images without losing too much high frequency details. In addition to denoising, the LFPM5D filter was extended to light field spatial super resolution, which is the task of upscaling the light field images while preserving the high frequency details. As I mentioned earlier, light field capture with plenty camera have a low spatial resolution. Thus, super resolution is a very useful tool for these light fields. In this example, we show the benefit of applying our enhancement pipeline before applying super resolution. Indeed, on the left, we have the result without the pipeline, where the noise is actually amplified by super resolution, while the result with our pipeline on the right is sharp but not noisy. Once again, the super resolution filter is not limited to plenoptic camera post-processing and can be applied to light fields capture with the gantry, as in this example, or camera arrays. Here, for each scene, we have on the left the result of a simple bicubic upsampling, which is quite blurry, and on the right are super resolution results, which demonstrate the advantage of our method even with high upscaling factors. All the tools that I have presented so far can be considered rather low-level processing of light fields. So I'm now going to present a more advanced use case of light fields as smart assets, which is depth estimation. For this purpose, we propose a method adapting optical flow estimation between the views of the light field, which corresponds to disparity estimation. One of the recent improvements to our depth estimation method was to design a binary descriptor called SABOM, specifically for matching between light field views, which exploits the 2D angular gradients of the light field in addition to the 2D spatial gradient. This descriptor is very fast to compute, so as shown in these results, we can obtain a similar disparity estimation quality to existing descriptors such as SIFT, but we have a much faster processing time. Once the disparity of a light field has been estimated, thanks to calibration tools developed, for example, at BRNO University of Technology, we have access to the camera parameters, and the disparity can be converted to a metric depth map. Once we have a metric depth map, we can represent the scene as a point cloud, as in this example taken from the interdigital dataset, which was also captured with a camera array. On the left, we show the point cloud obtained from the light field images, which are shown on the right. Scene reconstruction is interesting in itself, but the depth estimation on such light fields captured with camera arrays can be challenging due to the wide disparity between the views, which results in visible artifacts in the point cloud and a very sparse representation. Nonetheless, it can be a very useful visualization tool, which brings us to another of the tools that we contributed, which is light field refocusing and user interface for light field refocusing. In this example, we show on the left a refocused image where the focal plane is at the back of the scene, which is illustrated by a blue plane on the point cloud on the right. When moving the focal plane, as for example here to the middle of the scene, the point cloud gives the user an intuitive interface to appreciate the precise localization of the focal plane in the scene. Getting a good understanding of the focal plane position is not always easy from the refocused image itself. In this example, the focal plane is aligned with the painting on the right of the scene and was selected by the user directly on the point cloud, as shown on the right by clicking 3 points belonging to the plane of interest. This example also illustrates why light fields are interesting as smart assets, since producing a tilted focal plane normally requires a specific lens, but can be easily generated algorithmically from the light field. Finally, a challenge that we face when applying refocusing to sparse light fields captured by camera arrays is the angular aliasing. Here we show an example of refocusing on the front of the scene, and as you probably noticed, the defocus area, which is expected to be a smooth blur or bokeh, appears instead very rough and irregular. And this is because of the sparse sampling over the angular dimension. So we've developed an anti-angular aliasing filter, which is based on the depth information in order to obtain much more natural results as shown here. As a last illustration of reuse case for light field assets, in addition to the focal plane position, we can also play with other refocusing parameters, such as the size of the synthetic aperture, which influences the strength of the defocus blur. In this example, we have the same focal plane as in the previous slide, but the synthetic aperture size was reduced, which also reduced the strength of the blur. This is now the end of my presentation, so thank you very much for your attention. And next, we have Dave from the Foundry.
Hi, I'm Dan Ring from Foundry, and as part of SAUCE, we extended our Flix software. Flix is a storyboard development tool for collaborative work in animated film, TV, and gaming that promotes fast-paced collaboration by removing technical barriers that slow production down. Flix is currently integrated with specific industry-leading applications such as Photoshop, Storyboard Pro, Avid, and more. Flix was extended beyond just storyboards so that its data model around asset storage can be used in new contexts in more stages of the post-production pipeline, such as lighting, texturing, modeling, animation, FX, and compositing.
The first stage of any asset library system is deciding how and where to store the data. There are many ways of doing this, from simple file system-based network storage to relational object database storage systems. In this section, the design decisions and features of the developed storage system are presented, all of which have come from real customer requirements and have been implemented in Foundry's Flix software. These features could be a minimum checklist for anyone thinking of writing their own asset storage system. The first, and possibly the most interesting lesson learned from customers, is that creative people don't want to work with files. In the same way that something like iTunes doesn't show you the underlying MP3 files, if you're working in a modern pipeline, the asset store should manage the handling of files for you. Once the asset is imported into the storage system, the user should not need to know anything about the underlying file or where it's stored. To make assets useful, there are two additional properties and constraints that an asset should adhere to. That is, an asset must relate to a single, uniquely addressable entity, and an asset must also be versionable. The second important lesson, and a key feature that defines a storage system of the future, is that artists should not need to know what data type or format the asset is stored as, only what they can retrieve the asset as. This ensures both forwards and backwards compatibility with various file formats, and is enabled by a transform engine. This is one of the key features of this work. The transform engine implements a plugin architecture to enable parsing and transformation of assets. For example, if an asset was imported as an FBX file, it could be retrieved as an OBJ for compatibility with legacy software. Similarly, it could be automatically converted to an Alembic file or conformed to the Studio Pipeline's USD format. Here is a demonstration of the transform engine in practice, as implemented in Foundry's Flix storyboarding software. In this demo, we're going to import a USD asset and use the transformation engine to render a thumbnail of the asset so that it can be visualized in Flix's UI. The transformation in this case is enabled by a plugin, which has been uploaded by the Flix client to the server. Now let's look at the asset we're about to import. It's the familiar USD kitchen scene, with the addition of an animated robot and a keyframed camera, where each keyframe corresponds to a story panel that we want to work with. Now when we import the asset into Flix, the USD plugin is invoked. It triggers a render of the scene from the scene's camera at each of the camera's 5 keyframes, using the Embry renderer. Once rendered, the thumbnails are used to display the scene's content, but crucially, the underlying asset is still a USD file. I've just shown that knowing the type of an asset can be valuable. However, the variety of file types in VFX and animation studios is staggering. A key requirement of an asset library is that imported assets cannot be limited to known file types. Each asset should be stored regardless of file type, with the provision that if a file type is known to the system or becomes known to the system later on, it can be operated on in some way. When an asset is requested from storage, it needs to be easily accessible. This has been implemented through a simple and well-documented REST API. Modern pipelines and infrastructure can be heavily customized. Therefore, having a well-used language and software-agnostic way to retrieve assets is vital. The storage system must provide redundancy and load balancing to guarantee performance. We achieved this through server-side replication policies, 2 of which we found to be most effective. The first, a copy-all policy, ensures that data is copied to all sites, ensuring high-performing multi-site operation and high data redundancy. A don't copy policy ensures data is not automatically moved between servers unless requested by a client. This helps reduce unnecessary replication of assets and is very useful when multiple sites, or even multiple servers within the same site, are being used for different shows, for example. The cloud is becoming more and more attractive for collaborative data access, particularly where data needs availability, redundancy, and performance guarantees. While concerns around cloud security are easing, there is still cost, knowledge, ownership, and integration barriers that mean customers often prefer to keep data local. The presented system has been developed to operate both locally on a facility's existing infrastructure, as well as in the cloud, or even a hybrid of the two. And lastly, the storage system needs to work in modern VFX and Animation Studio pipelines. This means that all of the above features must be delivered through the storage system alone. For example, while cloud-based load balancing and replication services could be enabled by running the storage system in the cloud, some functionality of these features must also exist without third-party services. The idea is that the system should be able to work independently and work easily for both large facilities as well as small studios with no IT departments. This has been achieved largely through containerization and an intimate understanding of customer infrastructure to minimize deployment issues.
Now that we've presented how assets are stored, the next challenge is how to efficiently classify them. Over to Disney researchers Heiko Riemenschneider for more information.
Thank you, Dan. I'm Heiko from Disney Research Studios, and I will briefly review some of the machine learning work. Smart assets are any 3D models, videos, props, etc., which are enriched with useful metadata and can be used for smart tasks like searching or automation. Machine learning was used to train neural networks for classification and labeling tasks, and to extract information from an asset to add metadata. Example use cases may include 1. Labeling an asset file with its content. For example, this is a sports car, or a racetrack, a tree, or a specific character. 2. Segmenting 3D scenes and objects into their parts. For example, a humanoid into arms, legs, or a city into buildings, parks, streets. And a third example, as already mentioned by Filmakademie, is about identifying the mood of a scene. For example, if a region is a scary alley, or a cozy park.
Thank you, Heiko, for the kind introduction. My name is Trevor Canham, and I will now present the work from the Image Processing for Enhanced Cinematography group at the Universität Pompeu Fabra, conducted by myself and my coworkers under Marcelo Bertamillo. As you've seen throughout the session, the SOS project is all about making assets more versatile so that they can be reused in different creative contexts. For our part, we aim to do this by creating an array of transformation tools which can be used to repurpose assets in different color encoding contexts. Before explaining these tools, though, I'll first explain what I mean by color encoding context. Since color is a perception and not a physical property, to fully describe the color encoding context of a piece of imagery, one must account for all of the factors relevant to the visual process. This includes not only the physical values being generated from the display, but also data regarding how the display is viewed, the environment in which it is viewed, and who's viewing it. Otherwise, your colors are only reproducible on a specific display, viewed under a specific set of conditions by a specific observer. Today we will present a series of tools for transforming between color contexts that fall under two separate categories of color encoding. A set of tools for easily moving between device-dependent spaces during the production workflow, and another set for translating mastered imagery considering these perceptually relevant factors. Throughout the course of this project, we continue development on a tool which matches between shots of the same scene with unknown encodings by optimizing the parameters of a generalized camera encoding pipeline to make a match between scene correspondence points. For the case of gamma-encoded imagery, we simply optimize for a nonlinear gamma component and a 3x3 color transform, looking for the best match between source and reference correspondences, which we find via the SIFT method. We also developed a formulation to account for the standard encoding pipeline of logarithmic imagery. One can see that the methods make a good qualitative match, and quantitative results showed that it outperformed a number of academic alternatives. You can reference our IEEE Transactions on Image Processing publication to learn more. Throughout the post-production process, we make adjustments to imagery to achieve a stylistic interpretation of reality. This process is called color grading or color correction, as I'm sure many of you already know. After these corrections are made, the connection between the imagery and the scene light is no longer relevant, as we have a new artist-approved reference point. so it can be useful to adapt outside content into this stylized context. But since we don't have any model of how imagery was translated from seen light, and we potentially have no correspondence points between the reference and test image, we approach this problem quite differently compared to color stabilization. Instead of trying to go back through the pipeline, we go in the opposite direction, making different perceptually based matching transforms from the source to the reference for luminance distribution, color alignment, and local contrast. The results show a photorealistic transfer of the color grading style, although in some cases artifacts arise from the scene content of the reference. You can check our SMPTE publication for more information on this method. Our next set of tools aim to emulate perceptual processes to translate the appearance of mastered imagery between viewing contexts. This process is akin to color appearance modeling, where a chain of transforms mimicking visual processes, mostly limited to the signal processing blocks in the retina, are applied given the parameters of the input condition to achieve an encoding which aligns with perception. Then, if possible, the processes can be inverted and applied given parameters of the output condition to translate the appearance of an input imagery between the input and output conditions. We aimed to create a practical version of this where the goal is the round-trip process and the perceptual representation is skipped so that we can validate each of our steps by the quality of the match between the source and destination representations. So we take each of these steps as an opportunity to account for a specific color context attribute which could vary between destinations in a practical motion picture distribution scenario. We'll walk briefly through each of these steps now. The retinal absorption step dictates the spectral interaction between scene physics and the spectral sensitivity and transmission properties of the eye. Normally this is addressed through the use of a single standard function shown in the graph on the bottom left. But in reality there is a wide variability between observers, exemplified by the plot from Asano and Fairchild on the upper left. They proposed a scheme for grouping this population of observers into a limited number of categories, which observers can be assigned to via a matching experiment. In our Society of Motion Picture and Television Engineers publication, we demonstrated a pipeline for incorporating these observers into a motion picture color management workflow. Through a simulation, we showed how these categorical observers can improve accuracy in color management by comparing the average population error between calibrating displays using personalized observers versus using a standard observer. The results suggest that this variability can cause significant color rendering errors, which should be accounted for, given that this is the first step of color representation. Chromatic adaptation is a process by which our visual system accounts for changing illumination color to preserve object color appearance. Since we assume for our application that imagery already has its intended color balance, we use this step to account for chromatic adaptation to surround illumination in the viewing environment. We conducted a series of psychophysical experiments to characterize the influence of surrounds of different color and brightness on the appearance of natural images, using a similar cadence to what is shown in the video. The results showed that the surround illumination significantly influenced the observer's adaptation point for all conditions tested. Using the data from these experiments, we developed a model to predict and account for this influence. The model is centered around the white point of the display and returns the degree to which the surround is influential based on the difference in display white point and ambient illumination color and the ratio between the ambient and display luminance values. You can read more about this work in our London Imaging Meeting publication. Our visual system compresses the dynamic range of real scenes, the difference between the brightest and darkest parts of the scene, so that it can represent them fluidly with its limited bandwidth. So we replaced this step with tone mapping operations which similarly aim to compress or expand the dynamic range of imagery to account for the capabilities of different destination displays. The major advancement of our method over common nonlinear processing operations is that we account for the fact that the nonlinear response is adapted to the mean luminance level, and it differs on either side of it, like the plot shown on the left. We've developed different variations of the method for specific applications through collaborations with RE, NHK, and the development of our own OpenFX plugin, shown in the video. Through our implementation efforts, our methods were developed with constant feedback from cinema colorists and have been validated in post-production scenarios. You can read our Multimedia Tools and Applications publication for more information on these methods, as well as our Journal of Vision publication, which addresses the theoretical background via statistical analysis. In the later stages of retinal processing, signals are pooled together spatially to execute higher-level processes. In these operations, the interaction between the size of the pooling field and the spatial frequency or size or field of view of the display can cause shifts in appearance. This is exemplified by how the effect of induction, the process by which the color appearance of image regions are affected by their surroundings, changes with respect to presentation size. In the patterns on the screen, the central ring on the left has the same physical code value as the central ring on the right. As the size of the pattern changes, one can see a shift in color in the central ring on the left. So we aimed to make a spatial filter which accounts for this by collecting psychophysical data on observers' perception of these effects at different reference sizes by asking them to adjust the ring on the right to match the left for each pattern, and later optimizing a filter to predict the correction between sizes. While our filter successfully predicts the observer responses from our experiment using synthetic patterns, its effectiveness with natural images is still limited, as this scenario adds multiple additional layers of complexity. In the meantime, we have a preprint journal article available on arXiv, which you can read for more information on this research effort. Alternatively, this step can be used for gamut mapping, where we compress or expand the local color contrast properties of an image to best preserve its appearance between renderings on displays with different capabilities with respect to the range of colors they can reproduce. The model takes the form of a center surround filter to be applied to the saturation channel of an image. Separate methods were developed for reducing or expanding the gamut rendition of images, each adapting kernel parameters according to the saturation properties of the input image. The method results were thoroughly validated against academic alternatives in a post-production scenario by cinema colorists. However, many preferred their in-house solutions, given that gamut mapping quality often comes down to a trade-off between preserving image detail and color appearance, which relies on the personal taste and aesthetic judgment of the artist. For this reason, we have developed an OpenFX plugin version of this method, with which artists will be able to use the method at their own discretion. You can check our publication in IEEE Transactions on Pattern Analysis and Machine Intelligence for more information on this method. There is a saying in imaging science that you can't really know anything about imaging science until you know everything about imaging science. The same is true of visual perception, or any complex phenomenon which is composed of numerous intimate interdependent processes. And for this reason, accounting for just one of them to homogenize between different color contexts often produces different variations on an imperfect match. When one cannot achieve a perfect match, it's left to the artist to decide which imperfect version best serves the aesthetic. For this reason, we simply try our best to provide artists with tools which give them greater control in adjusting content such that it can be adapted to new color contexts. We hope that you enjoyed our presentation and that you follow our updates in producing these tools. We'll now move to the presentation of William Greenlee from Double Negative.
Thank you, Trevor. My name is William Greenlee, and I work for DNEG in the Production Technology Department. I'm going to discuss some of the common challenges facing visual effects houses when trying to search for and reuse assets across a variety of asset management systems, and then explain how the source framework addresses these. In the case of DNEG, the company has millions of assets spanning decades of production. The cost of getting a human to manually curate every one of these assets could be phenomenal. Furthermore, curation is invariably inconsistent. Different teams have different ways of curation, and from a search perspective, these are not uniform or interoperable. The Source project seeks to address these issues by providing a framework for classification, search, and transformation of reusable assets. The Source framework is split into a number of constituent parts, all of which are separate and independently deployable, namely a contribution framework, execution framework, and search framework. The contribution framework provides the means for individual contributors to develop and share vocabularies, classifiers, and transformers in a consistent and interoperable way. Vocabularies, classifiers, and transformers are deployed into the execution framework, where their capabilities can be advertised for classification, transformation, and an implicit and explicit chaining. The outputs of the execution framework, along with available transformation options, are ingested into the search framework and made available to the end user via search user interface. All of the aforementioned components depend on a variety of subsystems for network, security, storage, and compute, which are provisioned as platform primitives. One of the fundamental ways we address many data-related problems is by canonicalizing our data and adopting a mature and established set of data standards, namely the linked data standards. These standards form the basis of our asset data model and provide a means to extend this model with vocabularies and ontologies in a decentralized and autonomous way, without the need for consensus or agreement across teams or departments, whilst at the same time maintaining interoperability of models, allowing partners and domain experts to contribute specific vocabularies, ontologies, and models for different types of asset, e.g. rigs, meshes, animations, etc. These standards also allow us to leverage and take advantage of a number of existing vocabularies and dictionaries, i.e. WordNet, Wikidata, and Schema.org. By using these, we don't have to invent tags and terms for describing things, taking advantage of established knowledge bases and only extending them with industry or organization-specific concepts and vocabularies. These vocabularies form the foundation for the classifiers and transformers. This allows asset and domain experts to leverage machine learning and introspection to train models for classification and enrichment. Instead of training and classifying using traditional machine learning techniques, namely string labels, we train and classify against concepts found in our vocabularies and dictionaries, thus augmenting and complementing our classifiers with established knowledge bases and enabling greater levels of interoperability, thereby exponentially increasing their effectiveness and value. Furthermore, by leveraging axioms and concepts in our dictionaries and vocabularies, we can materialize synonymity, hyponymity, similarity, lemmas, and inflection. The execution framework allows classifiers and transformers to be executed, and to also provide a means to chain together classifiers and transformers implicitly and explicitly across a variety of runtimes, enabling visual effects houses to compose complex classification and transformation networks. The outputs of these networks provide the inputs for the search API and user interface. The resulting enriched assets are exposed via a rich and expressive graph traversal search API. The transformation framework also allows contributors to express transformation options and transformation capabilities, thus widening the search results and including search results that could be achieved through one or more transforms. Finally, an extensible and intuitive search user interface allows artists to efficiently search and retrieve assets, leveraging the search API. The following screenshots demonstrate some of the key features of the user interface. The user interface allows users to search by full text and tag. In this sense, the search is to find assets with depictions that have titles or labels that match the search criteria. The Auto-Suggest API provides suggestions against the complete set of labels associated with all depictions, which a user can select or continue typing. If a depiction is selected, it is added to the search box as a selected label, and results are filtered by the selected label. If not, then a full text search against all the text labels and titles are made, matching results according to the pattern matching rules. This includes rules for exact matching, partial matching, lemmatization, and inflections. In addition to the text and tag search capabilities, there is also a multifaceted type descriptor that enables the underlying type system to be exposed to the search user interface. By adding and extending the vocabularies, we can create types of asset and depiction that can be materialized during ingestion and classification, and users navigation and filters in the user interface. The UI contains a number of filter controls that allow users to search by properties of assets or depictions. This allows users to filter results by specific values, scalar ranges, or enumerations of values. Again, these are informed by core and contributor vocabularies that are aligned to a core user interface vocabulary. The user interface also includes a map view, which allows users to search for assets based on the geographic location of the associated depictions. In this case, if the asset is depicting a landmark in New York, such as the Statue of Liberty, then selecting the United States of America should include the aforementioned asset in the search results. Along with geographic search controls, the user interface also includes a chronological timeline that enables users to search by relevant date or date range. This searches assets with associated depictions that have an associated date matching or within a date range. Knowledge bases such as Wikidata and Schema.org form the basis of the geographical and historical data created as part of classification and enrichment, and research supports a variety of properties that materialize during this process. Thank you. Finally, the user interface provides a number of controls and modalities for searching by similarity. The first scenario is when a user has searched using certain tags and wants to broaden their search results to include assets that have depictions with synonyms matching the tag. The second context for search by similarity is when the user has found an asset and is viewing it, and then wants to find assets similar to that asset. In this scenario, a number of attributes can be used to find assets with similar attributes depending on the current search context. If type, filters, and tags are already specified as a search criteria, then these are included in the similarity. Otherwise, the default behavior is to find assets and depictions of a similar type with similar tags to the selected asset and its associated depictions. The user interface also provides a class navigator, allowing you to traverse assets by class hierarchy. This allows assets of similar types to be grouped in search results, along with a means to narrow broaden the search results by relationships between classes. This gives you hopefully a comprehensive overview of the source framework and its constituent parts. Thank you very much.
Hello, I'm Ewan Rice. I'm a software developer on the crowd R&D team at DNIG, and this is our work on a constraint-based motion solver and animation footstep cleanup, which were part of two research projects funded by SOS and aimed at expanding our animation editing tools and reusability for crowd artists. Crowd shots can require hundreds or thousands of characters following their own paths over varied environments and carrying out actions with precise timing, and they're quite often subject to change throughout production. So it's not feasible for every character to have authored animation from the animation department. So crowd artists need the tools for runtime editing to blend, loop, trim, layer animations for many characters. And with a growing trend of crowd characters being much closer to the camera, there's also need for producing higher quality animation. Firstly, I'll be showing our solver for creating locomotion animation from user-defined constraints. Here we are placing spatial constraints to form a path for the character to follow. The solver will firstly create the best animation it can find from input mocap animation. It will then edit the path of the animation with minimal deformation to reduce foot sliding. We primarily use Houdini as our crowd solution at DNIG. We have created tools with viewport interaction in Houdini that are integrated for current crowd tools, although the solver itself is DCC agnostic. The solver works in two parts. We input constraints and animation to the solver, which first go into a motion graph. A motion graph automatically finds good transition points between animations and forms a searchable graph that can create endlessly looping animation. Given the constraints, the motion graph evaluates what the best animation it can create that adhere to those constraints. But there's only so much mocap that we can provide. The output animation won't be able to follow any continuous path. We still need to edit the path of the animation to follow those constraints. For this, we use a Laplacian shape deformer, which is a solver for linear systems and attempts to minimize changes in the edges between the points of our animation path. This allows us to make these kind of macro edits while maintaining the shape of the path, and in terms of animation, that helps reduce foot sliding. On its own, a Laplacian solver, as you can see, can really stretch out or squash the animation. So it's a combination of a motion graph and Laplacian solver, which is necessary to really build high quality animation. The solver is quite flexible and extendable for additional constraints beyond just spatial constraints. Here, by placing spatiotemporal constraints, which sets the position of an animation at a given frame, and inputting both walk and run animations to the motion graph, we get a transition from a walk to a run. Motion graphs are also well suited to adding label constraints, where pre-labeled animation can be chosen during set frame ranges. Although we use a linear system solver, we can still solve non-linear problems such as collision avoidance by iteratively using this Laplacian solver and adding spatial constraints to move colliding paths apart. The second project we worked on was for animation footstep cleanup and terrain adaptation. Terrain adaptation is crucial for crowd work where characters need to be able to reuse the same animations to traverse any uneven terrain. And with a system like the motion solver, where many animations are being blended and their paths deformed, we can introduce foot sliding. Here's an example of what we mean by foot sliding. This is an animation created by the motion solver where the path is very stretched out, resulting in very noticeable foot sliding. And here we're able to apply footstep cleanup to lock the feet when they're in contact with the ground. So to do this, we first need to detect when foot joints such as the heel and the toe are down on the ground using a simple speed and height threshold. Then we must find transform targets for the ankles, which keep the joints in place when they're down and above the ground, while also allowing the foot to roll as it does in the source animation. Then use those ankle targets as end effectors for a constrained IK system that will create a realistic pose for the skeleton. Here we've applied the cleanup to uneven terrain, where it's also important to smoothly move the hips to ensure that both legs can reach their targets. We also allow for leg lengthening with user-defined constraints. For stairs and terrain where with the discrete changes in height of the surface, we also apply spring dampening to the root joint of the animation. This is ensure that we don't get any noticeable pops when we move from one step to the other.
There's still plenty more to do. For the motion solver, as with all our artist tools, extending the Houdini tooling and workflows is a continuous task. There are more constraints that can be added that can allow for interaction between agents, temporal editing, and tools to be able to generate seamless blended animation backwards from a set pose that is anchored in time and space would be very, very valuable to our crowd artists. It's also important to give the artist as much control as we can. Tools that automatically create animations are useful, but we still need to be able to give artists control to edit as closely as possible and incorporate animation that's been manually chosen and edited wherever needed. Motion matching is another data-driven animation system similar to motion graphs that could provide a faster alternative, as searching a motion graph can exponentially increase in complexity with the density of the graph. With the IK system developed for the Footstep Cleanup, we can also start to implement animation retargeting on different sized skeletons. And for constrained IK rig available in crowd scenes, we provide keyframed animation for the crowd artists, as well as offering tools for procedural animation with look-at, counterbalancing, or physically driven animation. If you'd like to learn more, these papers serve as the inspiration and basis for these projects. That was everything. Thank you very much for listening. I hope you enjoyed it.
Thanks, Jon, for the presentation. Another animation toolset that we have developed as part of the SOS project is the auto-skeleton for a fast pre-roll workflow. My name is Retrieval, and I am a researcher from the Reasons Group, Trinity College, Dublin. When we work in visual effects shot, the animation is normally provided by the animation department as geometry caches with no rigging information for efficiencies and compatibilities across different companies or pipelines. The given animation typically consists of the actions happening between when the camera starts and when the camera stops. However, we often need to know what happened right before the camera began rolling in order to create a correct or realistic effects element. So we have to send back the animation to the animation department and request a pre-roll to be added. The turnaround time is unpredictable depending on the schedule and what the animation department have agreed on during their bidding process. Alternatively, the effects department can create the pre-roll themselves, and if there are tools readily available to do so, that would be a huge time saver. DNEC and TCD have come up with a few ideas to repurpose existing animation to create a pre-roll animation, and one of them is an auto-skeleton toolset. This utilizes the knowledge of anatomy in creating an estimated skeleton structure of a human character. The skeleton generators can be used with a T-pose, and it also can be instantly transferred to any given poses. Within the toolset, we also have other tools to interpolate the skeleton poses, replace or modify them in place, creating flexible workflow for a pre-roll motion clip. The skeleton generator can also be used with the newly introduced KineFX workflow in Houdini 18.5.
Thank you, Pursuit. Yes, my name is David, and I'll be talking about the crowd simulation work that Trinity College Dublin have done as part of the SOS project. So the diagram on the left shows the setup that we have, and so at the start of the SOS project in proposal, we defined what we'd like to be able to do, and that is to take a semantic environment and a crowd with some data about the crowd, so semantic data, which applies to the crowd, and to be able to use the semantic data in the environment and then calibrate the crowd so that the crowd behavior is driven by the environment semantics. So you can see here that if we swap out our semantic environment for a new one, that the crowd should update its behavior to use the new semantic environment. And similarly, we should be able to use another crowd and calibrate it against this new semantic environment. And so to do that, we've defined some integration / configuration crowd simulation software. And so our goal is really to use semantic information to drive crowd behavior. So the first thing we have to do is process semantic data for use with our framework. So the problem that we were initially faced with is that semantic data comes in forms which vary in structure. So that can be, we can get JSON, CSV, TXT, and they can also have different ontologies within the file structure. So really we need a uniform way to store and process this data, and the reason for that is AI modules need to know what fields are expected in order to run successfully. So this is often referred to as the context of the data. So if we have a parameter called number of crowd agents, that should be an integer. New sources of semantic data may also become available as classifiers are developed, and these also need to be integrated. So we need to be able to structure the semantic data in this way so that we can add additional sources. So a motivational use case for this, we have this data set called Dublin City, which is an annotated LiDAR point cloud, and you can see the ontology defined. And then below that, we have a classifier trained on the cityscapes data set with its own ontology. And so we have an asset on the very left here, which is the Campanile and Trinity, and you can see that the two different ontologies can be used to describe this asset. But the problem we have is, how do we take these ontologies and provide some kind of consistent way for the AI decision-making modules to actually drive the crowd behavior? And so really the general case here is shown in this diagram on the right, where we have arbitrary sources of semantic data, and we need to be able to define a uniform interface to provide to the AI decision-making modules. So we can have arbitrary sources, and we also need to be able to define the structure for this data on the fly in some consistent way to integrate with existing modules and interfaces so that nothing breaks. If we add a new source of data, we should be able to transform it in some way so that the AI can still read and understand data. So the way we've dealt with this is using JSON and JSON schemas to validate JSON files. So using JSON as a file structure along with schemas allows as a consistent way to structure semantic data. So any JSON file can be validated against a corresponding schema. So we know that the schema acts as a template, and if the JSON file doesn't conform to the template, there's some inconsistency there which can be flagged before it's passed the AI modules. So the advantage of this is that it's human readable in JSON format and also machine parsable. So a human can go in and edit this JSON file very easily, and then a machine can still read it. We get structural validation of the data to ensure consistency using our JSON schema. We can always ensure that the JSON is properly structured, and robust and efficient libraries already exist, and they do all the heavy lifting. So we only have to do some kind of minor specifications, and the libraries will do the rest of the hard work. So here we have an example of how this can be used in Unity. So the first thing we do is we've selected a game object, and then we create the JSON file. So you can see that here, and the parameters that already exist are some defaults. The next thing we do is we create a script to allow us to read and write from this file easily. And a schema already exists for this, which we created in advance. And so here you can see some values being created automatically. And this can be checked in advance, so it can't be written to the file unless it conforms to the schema. So you can see here that it doesn't conform to the schema, so there's an issue and the file can't be saved. And then we can use this semantic data to actually drive the crowd behavior. So the way we've done that is using a potential field module. So a potential field can be thought of maybe as like a magnetic field where the agent is driven kind of as a particle through this field. And we can set up one field for multiple agents, and it gives us this slightly more natural looking path where it's not kind of jagged edges as you get with A star and others. So the way that we've done this is we've first specified a piecewise quadratic conic function which tilts the plane towards the goal, and then we've added some Gaussian distributions to provide repulsive bumps which are then kind of navigated around, and then we use gradient descent to find a trajectory because these two functions are both differentiable, and then we take a linear combination of the vector from the agent to the goal, the gradient vector, and momentum vector to update the agent's velocity. And that ensures that the agent will keep moving to the goal, avoiding some local minima and maintaining its momentum as well, so that there aren't any very sharp turns which are unnatural. And so we've implemented here a social distancing use case to demonstrate how this works. So first of all, we have to create the semantic data. So as before, we use our scripts to write data to a file for this game object. And you can see that we have the asset name and the object type is crowd, and then we have a repulsive value which tells the agent how far around this crowd to go. And then we can write this to a file and then check it against a schema to make sure that the AI can read from it. And once we know the AI can read from it, then we can set up all the agents to read from these files in order to tell them where to go. And so we have one potential field generated for all agents in the scene, and the agents can avoid these in a kind of more natural way than kind of having very jagged, sharp edges. And then we can retarget this by just taking these the same approach, but updating the position of these agent groups in the new scene, updating the JSON files, and for the semantically similar commuter style scene, it's very quick to set it up from the previous scene. We've also set up a motion capture classifier. So in order to develop these scenes, we need animations to play. And in order to do that, we need to search for animations. So a neural network classifier has been developed. You can see the confusion matrix on the right. So it's performing very well on the classes we've defined it for, which are bending down, jumping, running, and walking using an LSTM. And you can see on the left here demonstrated how it works. We have a BVH file, and then we have a classification server. And the client sends the BVH file to the server, and in return you get the predicted class which is running. And so here we have a video of putting this all put together. So you can see we have our scene with some post-processing added, and we have the crowd set up using our tool set. So the first thing we do is we annotate the scene using some JSON files, and then we generate the paths at a high level for agents. And this gives us the high-level navigation. The next thing we can do is search for animations using a database of semantically annotated animations, which can be imported and searched and imported into the scene. We've also implemented some local avoidance using the reciprocal velocity obstacles library, and you can see a demonstration of this here. And so we've put all of this together to create this scene quickly, and it gives us visualization capabilities. We have a lot of control of the crowd scene and compatibility with semantically similar environments. So that's it from me, and I'd like to pass you on to our next speaker, which is David Moreno from Universität Pompeu Fabra. Thank you.
Thank you very much, David. My name is David Moreno from UPF DTI, and I will present our contribution to the SOS project. Prior to technical details, I would like to introduce you a little bit about our work inside the GTI. We are a research group with a strong interest in different areas such as interactive 3D graphic tools and implementations, expressive avatars, as we could see in the bottom right GIF, and also on HDR on the web, as could be seen in the top right GIF. Both of these last two topics are researched in two Horizon 2020 projects, HDR for EU, and present. In order to introduce you to our work, I would like to contextualize a little bit. In the mark of the source project, we aim to work on pipelines to create smart assets, more specifically pipelines to generate virtual characters' identity through motion stylization and behaviors. Thus, there is the need to construct the behavior and its representation in order to use it in video games and virtual simulations. Regarding our specific goals, we could divide them into 3 main points. First, we wanted to bring closer behavior creation and stylization tools for those users who might not be really expertise, or for researchers which could not be really into programming skills. We decided to achieve that through graph programming easy-to-use pipelines on the web because of accessibility and understandability factors. Also, developing a robust JavaScript and C++ library to create and execute such behaviors was targeted as a goal, as well as creating an open repository of behaviors to enhance the collaboration and the data available. Now I'd like to show a big picture of the pipeline we have designed to achieve those goals. From left to right, the process is the following. First, the user creates or loads the graph, which in other words is the behavior, and also creates the scene with different virtual characters, paths, points of interest. After that, the behavior system decides for each virtual character which action it should perform, and sends the data to the animation model, which is in charge of animating and stylizing the animation according to emotional properties the virtual characters have. Finally, the animations are sent to the render engine. The outcomes for this project are, first of all, a standalone web-based tool, also called Medusa, which allows to generate schematic scenarios, populate them with unique world-aware virtual characters, create, load, and edit behaviors through a hybrid approach of behavior trees. This hybrid approach flows in a tree traversal way and also as a flow graph horizontally, modifying the classic behavior tree node properties such as dynamic targets or thresholds. Runtime modifications are supported and directly visualized in the simulation. This system has as a core the hp3.js library, the one developed for this project. Also, it is possible to stylize the virtual characters for the pose through the emotional stylization module. The performance is good even with 100 virtual characters with their own behaviors and stylization. Here we can see some simple snapshots of Medusa, which we will see later in a fast video. We can see the hybrid behavior tree editor and also the full interface. The following outcome we have generated on this project is an emotional body pose stylization system. We have approached this stylization in 2 different ways. Regarding the first one, we implemented a style structure from already stylized animations in order to transfer later such emotion to other different animations. The second approach relies on the valence arousal parameters, tweaking slightly the joints rotations of a virtual character. The following couple of slides I will try to detail a little bit more the 2 stylization approaches implemented. The first one, as I mentioned, extracted the emotion from stylized animations. That was done computing the difference between the neutral and the emotional animation. After that, the difference could be applied to other animation. So, after getting the rotations of the new neutral animation, we operated in the quaternions to apply such differences. In some cases, like in the idle, there was only the need to compute the difference with the first frame, as there were no significant variations along the animation. The disadvantage of this approach was that we still needed to have some kind of emotional or stylized animations. The second approach deals with this disadvantage, as with just single animation and without any extraction, we could achieve different emotions taking into account the valence arousal width. Depending on those 2 factors, relevant bones of the virtual character are modified after the animation is applied to obtain an emotional body expression. The relevant bones for this approach were the full spine, the neck, the head, the shoulders, and also the arms. Also, the energy of these animations changed slightly taking into account these parameters. We have also implemented this approach in a Unity component, so it is also available in this platform. Recovering the third goal I previously mentioned on the first slides, we also developed an open repository of behaviors, where the graphs are stored with a name, helpful in case the user put it descriptive, some tags, and a brief description. The behavior could be directly uploaded from Medusa or could be uploaded manually, by downloading the graph file from the tool and uploading it later. Also, Medusa is connected to this repository, so the user can directly load the behaviors from there. Moreover, to prove the usability of our implementation in more use cases, we have developed a proof of concept of a video game where all NPCs are controlled by our system. We wanted to test it outside the editor to validate the integration into other projects. To finish with the outcome section, I'd like to show a short video about Medusa. First of all, we can see how we can fill the scenario with virtual characters, paths, and points of interest. We can also see how to use the graph editor to generate the behaviors and how the properties affect in real time to the behavior. The virtual characters have an individual perception of its surroundings, and also they can interact between them. Finally, we played a little bit with the valence arousal parameters to show the different emotions we can achieve. Finally, we have some future work to be done in order to improve our outcomes. First, abstracting even more the hv3.js library would open a wide range of possibilities in other fields rather than virtual character behavior generation. In fact, we are already improving the library for slightly different purposes. Also, having a generic retargeting of these skeletons would allow several improvements on the animation side, as generalizing and improving the stylization, allowing masking to animate the virtual characters by body parts, and also be able to adapt to almost any virtual character. As the last future work improvement, making smarter nodes with some artificial intelligence would generate more unexpected behaviors, giving more realism to them. Thank you very much for your attention. Next, we have Jonas from Film Academy.
Thank you, David. So we here at Animationsinstitut of Film Academy Baden-Württemberg have been mostly involved in experimental productions, character animation, and virtual production use cases within the source project. Concerning light fields, we were able to set up a reference production in which we tested the possibilities of the light field rig created by University of Saarlandes and algorithms developed by our partners Trinity College Dublin and BRNO University in real-world conditions. A cellist was captured with the light field rig playing 4 voices of an original composition. The 4 voices were then combined again in post-production. For this post-production, we identified 3 main advantages of the light field camera compared to a traditional monoscopic one. First, we were able to select and even animate the position of the camera and thereby the captured perspective in post-production. Refocusing after shooting was another topic we looked into. Additionally, depth information can be extracted from the setup. We used the advantages of the captured material to adjust the depth of field even with a focus plane non-parallel to the image plane. This is normally achieved with tilt-shift lenses. All this was freely animatable and adjustable in post-production, opening a completely new world of possibilities. Here's the final version of the 2D video. Even before this studio light field shoot, we captured some test footage with the light field camera that we publicly released. You can find download information on our website. The material of the unfolding shoot, as we called it, was also reused by us for another experimental production. Light field material can not only be used for the creation of 2D videos with a lot of possibilities in post-production, but the true potential becomes visible when using it on 3D holographic displays like the Looking Glasses. Within Unity 3D, we created a scene involving the multi-view light field material and combined it with a 3D background scene rendered in real time. Another aspect we were highly involved in within the project is character animation. Since a couple of years, the R&D team here at Film Academy is actively developing the virtual production editing tools called VPET. Attached to an arbitrary host system like Unity 3D, the Foundry's Katana, or newly added also the Unreal Engine, VPET provides the possibility to explore, edit and animate 3D objects and lights directly on a virtual production set involving digital set extensions. All of this editing is synchronized between multiple VPET clients that can be used directly on set or remotely, even in augmented reality. Scenes provided in the industry-standard Universal Scene Description, short USD, can be directly used within the VPET ecosystem. A scene host reading USD and providing it to the tablet clients has been developed by us in source. Additionally, a character animation interface has been added to VPET. A user can select the character on the tablet and direct it either with a pointing gesture or the joysticks attached to the tablet. The directions are then being solved to bone animation by a separate animation engine running on the host system. This animation engine can be easily exchanged by using the developed API. For this purpose, the VPET streaming protocol has been extended to support skeletal animation streaming. For example, the hybrid behavior tree-based WebGL Studio tools introduced earlier by UPF can be used as an animation engine, or even machine learning approaches. Two additional experimental productions have been carried out by us involving the usage of large-scale LED screens. For our LED wall experimental production here in our studios, we used one of these machine learning approaches I mentioned earlier to drive our main character Woody. VPET was used to direct the character on set. Through the machine learning, the character was able to move in different styles and interactively react to the virtual scene surrounding him. For example, he automatically stepped across obstacles. Also, other source aspects have been tested within this experimental production. To train such a machine learning approach, Film Academy also created a motion capturing database with different walking styles that we released publicly on our website. In the LED cave built by Rent Event Tech in Mannheim, we ran another experimental production. We were able to test the pipeline of quickly exchanging background and lighting in a car shoot scenario. The assets were searched and selected within the search and transformation framework developed by Double Negative, and then displayed on the LED cave. Additionally, we ran first tests with a machine learning-driven character animation provided by UPF that was directed again in real time on our VPET tablet clients. Together with Disney Research Studios Zurich, possibilities to label not only all 3D objects in a scene but also entire regions have been developed. We call these mood regions as they classify which mood a specific region of a 3D scene is most likely to cause for a virtual character passing it. This information could then, for example, be used by an animation engine automatically adjusting the animation of the character based on the surrounding. This makes the character smart. And with that, I would like to end this presentation of all the aspects that have been addressed within SOURCE at Film Academy Baden-Württemberg.
Wow, this was a packed presentation with a lot of information. Thanks to all speakers and contributors. So I'm sure you have plenty of questions. To ask them, please use the chat function of our Zoom room, and we'll do our best to answer them. Well, this concludes our FMX Spotlight on the EU project SOURCE. I hope you were inspired and would like to take this opportunity to thank our speakers, the FMX Spotlight team, and my colleagues in particular. If you are interested in being part of such research projects, you might want to consider studying technical directing at Animationsinstitut of Film Academy. Visit our website for upcoming FMX Spotlight shows early next year. And we hope to see you for the full online event FMX 2021 Reimagine Tomorrow, which will take place May 4th till May 6th. Stay safe, stay healthy, Merry Christmas, and see you soon.